Now, the main focus of our this last lecture would be arbitrary matrices. Definitely now, as Susmita asked. So here, because we will not have even for normal matrices, the problems are there. So we will not have this nice inequalities always. Therefore, now we look at the weaker question, so as to say the continuity. Just recall this example. It tells me that forget about optimal matching distance and so on and so forth. So forget about that inequality. The function, I cannot get even two continuous functions that represent the eigenvalues inside. So then my focus really becomes, okay, let me ask the weaker question, are eigenvalues continuous? So you would have heard this phrase, eigenvalues are continuous functions of matrices. So what do I really mean by that? Are eigenvalues always continuous in every sense? In what sense I'm talking of eigenvalues are continuous? That we will now look at. So remember, eigenvalues are roots of characteristic polynomials. Characteristic polynomials are n-degree monic polynomials. So therefore, and any polynomial is fully identified by its coefficients. If I know the coefficients in the order, in the correct order, so if I know the order, given an ordered tuple, I have a unique polynomial. So n tuple, I get a unique monic polynomial. So therefore now, looking at eigenvalues of matrices or looking at the roots of polynomials, it's an equivalent problem in a way. Why? Now, as far as I am concerned with continuity, my coefficients of the characteristic polynomials, because these are just polynomials in the entries. So the way you calculate the characteristic polynomial. So these are just the coefficients are just polynomials of entries of matrices. So they are continuous. So therefore, now I will first look at the thing. So remember, my eigenvalues I'm identifying mostly as unordered tuple. Now here comes a remarkable result. The C and sim was the quotient space of with that equivalence relation with when we are identifying all the tuples which are same under permutation. So that is the C and sim with optimal matching distance is the quotient tuple. The quotient topology of CN. But what we will see here, and I say that okay, this so now what we see here, these two are homeomorphic. Cn and Cn sim are homeomorphic. Now you say that it's the quotient map is not even 1-1, but still I insist that these are homeomorphic. So this is a remarkable way. It's difficult to digest when we first hear, but that is the fact. So here I will be now going into the thing that my Cn and Cn sim are homeomorphic. How can I show that? And that is the way that I will be going to polynomials. Every polynomial, to every n-degree monic polynomial, I associate an unordered n-tuple of roots, counting multiplicity. So it becomes an unordered n-tuple of complex numbers. So an element in C and C. To every unordered n-tuple of complex numbers, I get the polynomial back. I can get the polynomial back. I get an ordered n-tuple of complex numbers. And that exactly I am having. Why is it so? Because to every complex polynomial, to every polynomial of n degree, I will have n roots. Why do we have this? Because of fundamental theorem of algebra. Do we have this in Rn and Rn sim? If I just don't go to C complex, I go to just work in real? No, because I don't have fundamental theorem of algebra. So Cn and Cn sim are homeomorphic, but Rn and Rn sim are not homeomorphic. So are not homeomorphic. Try to check that out. Try to show that. But so now coming to how are Cn and Cn sim homeomorphic? So exactly, I take phi from Cn sim to Cn given an unordered tuple. So corresponding to n roots, I have the coefficients of the polynomial. So alpha 1 till alpha n is going to a1 till an. Now, because my AIs, the coefficients of polynomials, are elementary symmetric polynomials of the roots. So therefore, every polynomial function is continuous. So my phi is a continuous mode. That I also understand. So, but now I will show in fact that my phi is a homeomorphism. And what? So anyone who teaches complex analysis or who has done complex analysis, this is a very nice application of Rausch's theorem. What does Rausch's theorem tell me? That I'm just giving a very specific domain here. So it's true for more general domains, but I'm just taking a disk. So f and g are holomorphic functions on the closed in a domain contained in containing a closed disk, and on that closed disk I have that mod of fz minus gz is less than mod fz for every z in the boundary of the disk. Then f and g have the same number of roots counting multiplicities. Polynomial functions, I can just now here just so now here I can just basically restrict my f and g to be polynomial functions. So I can just, so if you do not have holomorphic, if you do not know what is a homomorphic function, just assume that f and g are polynomials because I will be applying only for polynomials. Now, so this, how will I use Rausch's theorem and how will I show that? So what is our aim? Let us recall that phi is from Cn sim to Cn defined by phi of this unordered tuple alpha 1 till alpha n going to the ordered tuple a1 till an. Alpha is the roots of the polynomial with coefficients a1 till an. The polynomial is z power n minus a1 z power n minus 1 plus so on till plus minus 1 power n minus 1 an. So that is the thing. So here now what I do is, so what is I need to show, if I want to show that see, I will show that phi inverse is continuous. First of all, is phi bijection? That we just discussed. Given the polynomial, it's identified by its coefficients, the order tuple of coefficients. So, and given a polynomial, it has unique roots. So, and vice versa. If I know the roots, I know that the polynomial is x minus alpha 1 power x minus x minus alpha 1, x minus alpha 2 till x minus alpha n. And I know that by opening up this, I can know my AIs. So my AIs then become the elementary symmetric polynomials of alphas. That is the thing. So now I need to show, so if phi is bijection, I will show that phi is inverse is continuous. For that, what I need to show here? So here what I'll show, so that given epsilon greater than 0, there exists delta greater than 0 such that maximum of mod aj minus bj 1 less than equal to j less than equal to n less than delta implies phi inverse. So phi inverse of aj, that is the aj's will be the coefficients of polynomial z power n minus a1 z and so on. Baj are the coefficient of the polynomial z power n minus b1 z power n minus z power n minus b1 z power n minus 1 so on. And so corresponding roots be alpha 1 till alpha n, beta 1 till beta n. So we will show that in that case, d of alpha beta is less than epsilon, implies. So alpha 1 till alpha n till alpha n, unordered tuple, alpha is are the roots of the polynomial with coefficients a1 till a1, and beta 1 till beta n is the other roots of polynomial with coefficients b1 till bn in that specific order. Okay. So now here we need to show this. So what do we do now here? And we will apply Rauch's theorem. It's a very direct application of Rauch's theorem. We define, so let epsilon greater than 0 be small enough such that the circles gamma j with center alpha j and radius epsilon do not intersect. So what I do is gamma j is the circle all such that z minus alpha j is equal to epsilon. ठीक है? And my gamma j intersection gamma k is non-empty, is an empty set. So they are disjoint. Now what I do is I take capital gamma to be union of gamma j. So let's see, just view these are circles. So these are subsets of C. So just so now gamma, take union of gamma j. It's a finite union of circles. Every circle is compact. So my capital gamma is compact. Yes. Now what I have, my AJs. So let f be the polynomial. F of z is equal to that z power n minus a1 z power n minus 1 plus a2 z power n minus 2 plus so on plus minus a n. This is the polynomial with roots alpha 1 till alpha n. That is the thing. So now what I do, this mod fz, this fz has roots alpha 1 till alpha n. And gamma j's are not intersecting. So my mod fz is not 0 on gamma, on capital gamma. So let eta is equal to minimum of mod fz z in gamma. That is strictly greater than 0. It's a compact set. F is a polynomial. It's a continuous function. So it's never 0 on gamma. So my minimum is exactly attained, and its minimum is strictly greater than 0. Now, if you look at the function that takes any coefficients, so let's take an ordered tuple. So define Cn to the space of polynomials. So Cx, the space of polynomial complex polynomials. Cz. So Cz I will write. C1 till Cn to be going to the function polynomial z power n minus C1 z power n minus 1 plus minus Cn. Then in that case, what happens? This function is continuous because this is clear, it's continuous. So therefore, so what is the metric on Cz? The metric on Cz is the uniform metric, the supremum metric, supremum of mod Pz minus Qz, where Z belongs to, let's say, on gamma. So CZ is basically with the supremum metric, that is supremum Z belongs to gamma mod PZ minus QZ. This is the metric on CZ. Okay. This is a continuous function. So Cn going to Cz with this metric. So therefore, what I have, that there exists a delta greater than 0 such that maximum of mod Aj minus Bj 1 less than equal to j less than equal to n less than delta implies the supremum of, so that I can write mod fz minus gz is less than eta for all z in gamma. The supremum of mod fz minus dz, or I can write for all z in gamma. Okay. So now what I have? So here my mod fz minus gz is less than. So whenever maximum mod aj minus bj is less than delta, my mod fz minus gz is less than eta. And eta is less than equal to mod fz, because eta is the minimum for all z belong to gamma. So for all z belong, gamma is union of gamma j, the circles. So then I apply Rauch's theorem on each gamma j. So what is happening now? What do I get then? In each gamma j, I have the number of zeros, the number of roots of f and g are same, counting multiplicity, are equal. F and g by Rauch's theorem f and g have the same multiplicity, same number of same number of roots inside gamma j, that is this z such that mod z minus alpha j less than epsilon inside gamma j, counting multiplicities. Then what do I have? So so now I'm really done. That means let's now look at the number of roots of f in gamma j. How many roots of f are there in gamma j? Only alpha j. So let alpha j have multiplicity mj. So alpha j is the root of f. So alpha j has, let's say that alpha j has multiplicity mj. That means g will have mj roots inside gamma j. So let's take those mj roots to be beta, or let's say that to be some zeta 1j till zeta mjj. What do I have now? For each, so alpha j minus zeta 1, zeta ij will be less than epsilon. This is for every j. 1 less than equal to j less than equal to. So 1 less than, sorry, the alpha j's are the distinct roots. 1 less than equal to j less than equal to k. Sorry. So alpha j are the distinct roots. So they have done. Sorry, just note there is a change. So when we are talking of alpha j's, these will be distinct roots. I cannot otherwise have gamma j's to be disjoint, obviously. So the alpha j's are the distinct roots. So let's not take, so instead of alpha j's, we take, so alpha j's are the distinct roots. So alpha j has multiplicity mj. So each alpha j, so what exactly I want in the optimal matching distance? I match each root of one polynomial with exactly one root of the other polynomial. So alpha j has multiplicity mj. So alpha j is mapped to, so can be matched with zeta 1j, zeta till zeta mjj. So alpha 1 we can do is the zeta 1 1 zeta m1 1. Alpha 2 I can match with zeta 1 1 2 till zeta m2 2 and so on. And each distance is less than epsilon. So what I have a one-to-one correspondence between the roots of f and roots of g in such a way that their distance is less than epsilon. So I have that matching with the required inequality. So therefore what I get, that my roots are mapped. So my d alpha beta is less than epsilon. And for what? When my maximum of mod aj minus bj was less than delta. So this was the condition that I had to apply Cauchy's theorem, that mod fz minus dz is less than eta. So this was the condition that I had to use for applying. So I get the continuity here. Yes. So now what I have got? I have really got from this that my Cn and Cn are homomorphic. One thing I have got from here. But I have also got that my roots of polynomial, the roots of polynomials are continuous functions of their coefficients. That is exactly what we mean by phi inverse to be continuous. So roots of polynomials are continuous functions of coefficients. Now coming back to matrices. Coefficients of the characteristic polynomial are continuous functions of entry, they are matrix entries. So therefore, now, so what I have a composition. I have a matrix A. I go to the coefficients of the characteristic polynomial a1 till an. This is a continuous function. And from this, I go to the roots. So lambda, so the eigenvalues lambda 1 till lambda n. This I have just shown. This is why phi inverse. This is continuous. This is because every coefficient of characteristic polynomial is just a polynomial in the entries of A. This function is also continuous. So therefore what I get? I get that in both the composite function is also continuous. So now if I look at this A going to my lambda 1 till lambda n. So A going to lambda A. This is a continuous function. Lambda A, what is the matrix? So here this is the thing with MNC to C sim n with the optimal matching distance. Now here now here see, when I'm talking of the C sim n, so this is a continuous function. So at least, but what about that example 0 1 z0? There I said that there is no continuous function. So there what I was looking at, I wanted to look at that there are, can I get two continuous functions? So there what, so come back to this 0 1 z0. This thing az. And here I'm saying that there is no continuous function. Here I'm saying that the eigenvalues are continuous functions of matrices. The difference is, what is the metric? What is the space I'm taking here? Here, when in the above thing, in this thing, I am taking the optimal matching distance. In this thing, what I was expecting is to get two functions, lambda 1z and lambda 2z. So therefore, what I'm doing here, I am saying that, okay, I can order them in some way that lambda 1z is this, lambda 2z is this. So I can mention that I will take, so for every z, I have that this will be lambda 1 and this will be lambda 2. So I have a way of ordering. But when I'm talking of optimal matching distance, there is no way, there's no ordering. That exactly I was avoiding by taking optimal matching distance. So my optimal, so as far as I view my eigenvalues as unordered tuples, then my eigenvalues are continuous functions of matrices. But if I want to look at them as some way or the other as ordered tuples, so I want to order them, I want to have n functions of eigenvalues, there this example shows that that need not be the case in general. So that is the difference between what we should be really careful when we say that eigenvalues are always continuous functions of matrices. In what sense we are looking at, that is important. So now, but nevertheless, we will see that so we have discussed this. So yes, in two-way special cases, we will have that the eigenvalues are, so in what the sense we want the ordered, that n continuous functions, that the n continuous functions represent the eigenvalues of matrices, that we have in two special cases. One special case being, so we look at now if my matrices, so now remember, all Hermitian matrices have real eigenvalues. For Hermitian matrices, by Bayes perturbation theorem, I have a nice continuity result. So my eigenvalues are so in that those metric, it's even this thing. They are even Lipschitz continuous. But not every, it's not that only Hermitian matrices have real eigenvalues. There can be non-Hermitian matrices that have only real eigenvalues. So all eigenvalues are real. So if the matrix having all eigenvalues real doesn't imply that the matrix is Hermitian. Okay. So I take all matrices which have their all eigenvalues real. Okay. We take this set MRN. And now we say that, okay, in this case, I can actually get n continuous functions of eigenvalue, continuous functions of eigenvalues. How? Because, again, I have real eigenvalues. So I can order them. So now, one thing I know that if I'm looking at MRN to RN sim, by the previous thing that we have just shown, that phi, so through that phi, I will have that A going to lambda 1 A till lambda n A. That is continuous function with the optimal matching distance. But now here, what will be the optimal matching distance? Where will the, optimal matching distance tells me that there is a permutation where the minimum is attained. Maximum of mod alpha j minus beta tau j, that tau is there where minimum is attained. When my eigenvalues are real, can you guess where the minimum will be attained? That thing kind of thing we have looked at in Bayes perturbation result also. So my minimum will be attained when my eigenvalues, these are all real eigenvalues. I can order them in decreasing order. So if I just look at my lambda decreasing A to be the tuple of lambda 1 decreasing A till lambda n decreasing a. So yesterday we talked about this tuple. This is an ordered pair. This is now an ordered tuple. So ordered tuple. So this, if I take this thing, and now if I take mRn to lambda decreasing a. So sorry, mRn to Rn. This is my function defined by a going to lambda decreasing a. This is continuous. So basically I am getting lambda 1 decreasing a, lambda 2 decreasing a, lambda n decreasing a. I'm specifying the order. Why is it so? Let me give you the idea of the why this is so. So you will have a very good idea, and if you just keep on continuing, it's like an algorithm. So what am I saying here? I know by the previous result that my mRn going to Rn sim is continuous. If I show that my maximum of 1 less than equal to j less than equal to n mod lambda j decreasing a minus lambda j decreasing b is less than equal to d lambda a lambda b, the optimal matching distance between the unordered tuples, I am done. Then I know that again just no here so we don't worry about, so we do not need normality of matrix here. There's nothing to do here. In fact, in continuity, these hold nicely for non-normal matrices, arbitrary matrices as well. So that is the beautiful part. So here we are clearly not looking at the inequalities. So we are just now having the qualitative results. So now, here now what we have is, my mRn to Rn sim is continuous, and from Rn sim to Rn, that will be continuous. Because if we prove this inequality, that mod lambda j minus, if we prove this, maximum of lambda j decreasing a minus lambda j decreasing b is less than equal to d lambda a lambda b, we are done. I will show how we get that. I'll just show you. It's more like an algorithm, you'll realize. I will show just for the pair. So if I have, what I'm saying here, if I just take n to be 2, and then you can actually extend it to n by repeating the same process again and again. In finite number of steps, it will be over. I'll just take n to be equal to 2. What I want to prove that, so let's take that there are two numbers, okay, two pairs, a1, so a1, a2, b1, b2, okay, of real numbers. I take a1 to be greater than equal to a2, okay, and b1 and b2 are, I don't know the order. Now, yeah, okay, let's say also that b1 is also greater than equal to b2. Then what I have? Then you can see that if I take a1 minus b1, so just take the cases. So if b1 is greater than a1 and b2 is less than a2, so in that case, so if b2 is less than a2, in that case, my a2 minus b2 will be less than A2 minus B1. So A2 minus B1 and A1, the maximum of A2 minus B1 and A1 minus B2. Obviously. So A2 minus, so or I can just say that A2 minus B2 is greater than mod of A1 minus B2. If I have the other way, then my A1 minus mod A1 minus B1. So if B1 is greater than A1, mod A1 minus B1 will be less than mod A2 minus B1. So if I just change the order, I will not have the inequality. So what I'm saying here is my minimum will be only attained. So my if that A1 minus B1 will be always less than equal to maximum of A2 minus B1 and A1 minus B2. A2 minus B1 and A1 minus B2. And my A2 minus, yes. And my A2 minus B2 will be always less than equal to maximum of A2 minus B1 and A1 minus B2. So I'm saying it's maximum of A1 minus B2 and A2 minus B1. And A2 minus B2 similarly will be always less than equal to maximum of A2 minus B1, the same thing, and A1 minus B2. That you can check easily. So what if, so now if I have two ordered pairs, A1, A2, B1, B2, A1, A2 I order in the decreasing order, B1, B2 I just don't consider that B1 is written equal to B2. If I want to minimize the distance, I'll have to rearrange such that B1 decreasing and B2 decreasing, I have to rearrange. That only because of this inequality. So therefore now what I have is that if I have n tuples, I will take the first two coordinates, look at the distance, and then flip the thing. If the minimum distance is if distance is not less, I'll flip. Then I will take the next two coordinates, the first and second, then second and third and fourth, and n minus 1 n. Then I again go to the thing, and in finite number of steps, I will reach that my both the both the tuples are in decreasing order. I'll start with one of the tuples with decreasing order, and the other by flipping again, seeing the minimum, by flipping again, I will get that it's the second tuple also becomes in the decreasing order. So you can check this out. This is a very simple inequality thing. It's no analysis, it's no algebra, it's nothing. It's just playing with the numbers. So now coming to the a more subtle result, it says that, okay, now the second special case we have, if I'm not taking now MNC, the function from MNC, the space of all n cross n matrices, to the eigenvalues, to the unordered pair or unordered tuple of eigenvalues. I'm not taking that. What I'm doing is I'm taking matrices first as a function of intervals. So I take T going to AT of real, and T belongs to some interval. And then I'm saying that, okay, now I can get n continuous functions, lambda 1 t till lambda n t, that such that each lambda jt is an eigenvalue of at. So then just parameterizing my matrices, where real parameter gives me the continuity of eigenvalues, the n functions that are continuous n functions of eigenvalues. Just parameterizing the, so that's, so the, now, so, wow, so we will basically be, what we will be proving now here. So now see again, when I'm talking of this, I start with the result that my lambda, so I know that matrices to the C and sim with optimal matching distance is continuous. That is a continuous function. Where I want to now extend my thing, from Cn sim to Cn I want to go. So now basically an interval will actually help me out. So therefore it's enough to look at an interval function from an interval to I to lambda to the unordered tuple C and sim. And then I say that any function, continuous function from an interval I to C and sim with optimal matching distance, for any such function, I can have n continuous functions lambda 1t to lambda nt where t belongs to I. Okay, so that is my thing. Now, how will I prove this? So this will, so we will prove this. So we will have certain steps here. So let's take step one. First of all, we have observed that. So now here I say that getting n continuous functions, I use just for brevity, I just use a phrase. So that will, not every time I'll say that there will be n continuous functions of the lambda 1t to lambda nt. So in that case, just existence of n continuous functions from I to C, so t going to lambda jt will be called a continuous selection. So now in step one, I assume that there are two subintervals, I1 and I2. Are two subintervals such that lambda, that function lambda has continuous selection. So that means there are n continuous functions lambda 1t till lambda 1 till lambda n on I1 and I2. What about the union? Will there be a continuous selection on the union of I1 and I2? If I1 and I2 are disjoint, obviously there is no problem. But if I1 and I2 are not disjoint, so if, for example, there is a point T0 in I1 intersection I2, then what I have? See, when lambda, that is continuous, that is a continuous function. As an unordered tuple, I have the existence of continuous function. So lambda is there. So now so let's say that I have, for I1, I have continuous selection as lambda 1 till lambda n. And on I2, I have continuous selection mu1 till mu n. But so what will happen? At T0, they are the same things. So at T0, what will happen? My set lambda 1 T0, my set of, so my set, yes, lambda 1 T0 till lambda n T0, the unordered set, the unordered tuple, that is equal to mu1 T0 till mu n T0, the unordered tuple. Remember that. So that means, and when the two unordered tuples equal, when one is a permutation of the other. So that means that there is a tau in Sn such that my mu I is equal to lambda tau I at T0. Now see, if my lambda i's are continuous, my lambda tau I are just permutation of lambda j's. So therefore, my lambda tau I are also continuous. So now what I take is, if I take the tube, this lambda tau 1 till lambda tau n on I1 and mu1 till mu n on I2. Then as tuples also they are same. Lambda tau 1 is equal to mu1, lambda tau n is equal to mu n. So now I have that there is a continuous selection on I1 union I2. What is the continuous selection? Lambda tau 1 till lambda tau n on I1, mu 1 till mu 1 on I2. So I have a continuous selection. So that I have the thing. So therefore, now let's assume that I is a closed interval. So I will be done by using the compactness of the interval, that if I show that for every t naught in I, there exists a neighborhood of t naught such that lambda has a continuous selection in that neighborhood, then I am done. So in collection in that neighborhood. So let's say that neighborhood is I naught. Then you can say that okay, for every point there's an interval. Now by compactness we will have finite intervals. By step 1 you can actually combine all these intervals and get a single continuous selection. So basically what I need to prove now here is that there is exactly for every t naught there is an interval containing t naught which has a continuous selection for lambda. So what I need to show now, step 2. So let t naught belong to I. So so there exists an interval I naught containing t naught and contained in I such that lambda has a continuous selection on I naught. That I need to prove. That I need to just concentrate on that. There also, what I'll first do is I take let. So now how will I do this? I will prove by induction on n. N is the dimension. So we prove this by induction on n. So let K be the set of all t's in I such that lambda 1, so lambda t consists of 1 point repeated n times. Okay, so we will denote by k this thing. So that means my lambda t is just lambda 1, lambda 1, lambda 1, lambda 1. So that's lambda, 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 lambda. There's no two different points here. Okay, so lambda repeated n times. Now we prove by induction. So when n equal to 1, obviously n is, so by induction, so when n equal to 1, why my proof, my thing is trivial, obviously. I assume that the result holds, this continuous selection. So if I have I from lambda t, the I to lambda t, I and t going to lambda t, where lambda t is of dimension now m less than n, the result holds. Okay, for every m less than n, the result holds. So induction on n, this is the induction hypothesis. Now what I will be looking at is the what happens when I go to n. There I will only concentrate on t naught that do not belong to k. So my k was the set, again remember, so k was a set of all t's in I such that my lambda of t was just a singleton lambda, 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 lambda. Sum for some lambda. Okay. This is a closed set. So K is a closed set, isn't it? If I have Tn sequence, so Tn is basically all are equal. So my lambda of Tn will also will not have 2 points, two different points. So therefore my K is a closed set in I. So let L equal to I minus K. This is L is open. Let now T not belong to L. I will show that there is an interval here for this T naught. I will show that. For others, there is no problem. Okay. So I will just look at this L. I will just concentrate on L. Now, so T naught does not belong to K. That means there are two different points in lambda T naught. Yes. So let lambda not equal to mu belong to lambda T naught. Okay. There are two different things. So then let multiplicity of lambda be K. Obviously, because mu is also there. So my multiplicity of lambda is, so let it be K. So 1 is less than equal to K is strictly less than N. Okay. Now what I do is, so you take lambda, the distance of lambda with this lambda T naught minus singleton lambda. This distance. So just now assume that lambda T naught is a set. So what will be the distance that will be strictly greater than 0? So let it be some epsilon which is strictly greater than, obviously strictly greater than 0. This is just a finite set which does not contain lambda. Then what I have? Epsilon is greater than 0. Now, because t going to lambda t is a continuous function, therefore, there exists an interval I naught contained in I and T naught belong to I such that the optimal matching distance between lambda T and lambda T naught is less than epsilon by 2. Now, what does it mean? So there will be two lambda that element lambda had multiplicity k. So there have to be, because it's an optimal matching distance, there are k points in lambda t. The t belong to I naught. For every t belong to I naught, there are k elements in lambda t that are at distance at most epsilon by 2, less than epsilon by 2 with lambda. So then what happens? Because lambda is at a distance greater than equal to epsilon from all other points of lambda t naught. So what I have? So distance mod lambda minus mu is greater than equal to epsilon whenever mu belongs to lambda t naught minus lambda. So therefore what I have? I have now that let xi1 till xk belong to lambda t such that t for t in I naught such that I have mod xij minus lambda less than epsilon by 2. There will be these xi1 till xk. then mod xi j minus mu for other mu will be greater than epsilon by 2. Yes. So now what I have here, what I'll get is I can partition my lambda t into two sets, two multisets. One will be xi1 till xi k, and the other will be lambda t minus xi1 till xi k. So xi1 basically xi1 till xi k t, and xi1. So these are all, so t in I norm. So what I have done now for t in I norm, my lambda t minus, so intersection, sorry, my lambda t, just a minute. So my lambda t minus xi1 t till xi k t intersection this xi1 t till xi k t is empty. Now you'll say that, oh, this is so silly to write. It's so trivial. But remember, I'm not talking of sets. I'm talking of multi-sets here. So what does it signify with this sentence? That my xi1 till xi k, when they are at epsilon by 2 distance apart from lambda, they cannot be epsilon by 2 distance apart from the other points of lambda t naught. Therefore, these two are disjoint as multi-sets. And therefore now, for t in I naught, I have two functions. So I have for t in I naught, I have two functions. T going to lambda 1t and t going to lambda 2t. What is lambda 1t? Lambda 1t is the xi1 till xi kt, that are epsilon by 2 distance, less than epsilon by 2 distance from lambda. And this is lambda t minus as multiset xi1 till xi kt. And now both of these are continuous, obviously, because my lambda t was continuous. So my lambda 1 union lambda 2 is lambda. So therefore, by induction hypothesis, I have, so lambda 1 by induction hypothesis, lambda 1 and lambda 2 both have continuous selection on I naught. And so now what do we do? So both have contained, but I naught was contained in L. I just few away to start with those the points of K. If I just combine them, because lambda is continuous selection on I. So if I just take I naught union the point K, the points, this will remain continuous, because see, the whole problem is that ordering. But when all the elements are same, lambda, 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 the ordering doesn't matter. So K in K, ordering doesn't matter. So therefore, what I have is that on I naught union K, I have the ordering as the same. So this I naught union K, we have a continuous selection on I naught union K. And by step 1, the consequence of step 1, I can actually combine all also this and compactness and so on, and I have the thing that I can have the natural continuous selection on whole of I for lambda, and that's it. So the important thing that when I'm parameterizing my matrices with real parameter, I have continuous functions lambda 1 till lambda n of eigenvalues. That's the smart thing that we have. Now I will. So basically, I will skip the proof here. But one thing that in the last result that we intend to do, but so now when I saw said that okay, if my A and B are normal, then we do not have the inequality with the optimal matching distance. So no, the lambda A lambda B need not be less than or equal to norm A minus B. But locally, I have this inequality. What am I saying here now? If A is a normal matrix and B is any arbitrary matrix, in fact, so I do not need even normality of B here. B is any normal matrix, but what is the condition? That my B is close enough. How close? At least it cannot go beyond. So it has the norm A minus B has to be less than half of the distance between different distinct eigenvalues of A. So minimum of mod lambda minus mu, where lambda and mu belong to sigma A, lambda not equal to mu. So B is close enough to A, then I have d lambda A lambda B is less than equal to norm A minus B. This is in fact a corollary. So it follows from that what we did for the Hausdorff distance and what we did for this so the Hausdorff distance, what we did for. So this really follows from continuity of eigenvalues. So it's a very beautiful proof. If you want, if you're interested, you can go to again 6th chapter, 6.5 section of matrix analysis, Rajendra Bhatia. So it's a very beautiful proof. What all the prerequisites have been done. So just combine the Hausdorff distance result and the continuity of eigenvalues for the parameter. So the one of the consequences, see one thing that if I take any path TA plus 1 minus TA plus 1 minus TB. So this if I just denote by AT, this is a continuous map. Now eigenvalues of, so there now I can say that my we can get n continuous functions lambda 1t till lambda nt such that lambda jt are eigenvalues of AT. That is a nice, and it basically we apply this thing and Hausdorff distance estimate and we get the thing from here. But we will skip this. Just final remarks. Now, what about, so if I want to have arbitrary matrices and if I just a minute, yeah, if I just want to look at the distance between the eigenvalues and this A and B are arbitrary matrices, and I want to look at the distance, so optimal matching distance. So then, do I really expect anything, or what can I expect in fact? One example you see, you take n cross n matrix with diagonal 0 just above the diagonal, the diagonal above the main diagonal to be all ones, all zeros above, all zeros below. This is an strictly upper triangular matrix. What are the eigenvalues? Eigenvalues, so let's say this is A. So what are the eigenvalues? Eigenvalues of A are 0. So sigma A is just 0. Now look at A epsilon. What do you do? Again, the main diagonal is 0. The first diagonal above is 1. all above is 0, everything is 0 except the bottom left corner, you put an epsilon here. Okay, put an epsilon on the bottom left corner. Then what is the characteristic polynomial of a epsilon? Lambda power n minus epsilon. What are the roots? So at least what are the so so what are the roots of this so what are yeah. Yeah. What are the roots of this? Yeah. What are the what is the absolute value? So epsilon. So those are the epsilon power 1 by n, the nth root of unity. So the modulus of the absolute eigenvalues will be all epsilon power 1 by n. So if you look at optimal matching distance, because A has all the eigenvalue 0. So the optimal matching distance will be epsilon power 1 by n. What is norm A minus B? Norm A minus A epsilon is epsilon. So what we are picking up? Plus power 1 by n. Yes, we are not. So Professor Ajit Iqbal Singh has asked whether we are not worried about normality. No, this is strictly for. So the example is not normal. The examples here are not normal. So we are not worried about. So exactly we are looking at what happens when the matrices are not normal. For normal, I know that there is a constant factor, though it's greater than 1, but I know that there is a constant factor. But not normal, I can see that now what maximum I can have. My d lambda a lambda b can be in terms of norm a minus b power 1 by n. Epsilon power 1 by n is getting introduced. So it doesn't now, I don't expect something to be power less than equal to norm a minus b. It becomes a minus b power 1 by n. One thing is this. Then the other thing, take the now, obviously, when I'm talking of arbitrary matrices, it involves all kind of matrices. It involves normal matrices also. So now take A to be 0, 0 matrix, and B to be just lambda times identity. Then what I have, I will obviously the d lambda a lambda b is lambda, and my norm a minus b is also mod lambda and is mod lambda. So both of them are mod lambda. Then so I cannot, then in that case, I cannot say that d lambda a lambda b has to be less than equal to something, some constant times norm a minus b power 1 by n. I have to normalize this also. I have to take care of, it cannot be lambda less than equal to lambda power 1 by n. It cannot be. Now, that's a wonderful result that we have. So that says that we can get still some inequality. So here you see that it takes care of. So my d lambda a lambda b is less than equal to 4 times norm a plus norm b power 1 minus 1 by n. So 1 by n is getting cancelled by this, and times norm a minus b power 1 by n. So this in fact, the first inequalities, so where the factor was dependent on n, was given by Ostrowski way back in 1957. It took a work of many mathematicians, and then it was then finally in 1990, Bhatia, Elsner, and Krause, and then Krause basically got the factor 4. So, but it was not just one work. It's a consequence of series of results and improvements, slow improvements. So even gradually it was improved, and then it came to 4. Krause showed that 4 can be reduced to 3.08 also. So, and the Bhatia and Elsner Krause also showed that something less than 2 in place of 4 will not work. But again, like normal matrices, this is still an open problem. What will be the best factor here? 3.08 till now is the best factor, and that was way back in 1990s. So you can see that. So these are very interesting and problems. So that's still open for a long time. So that concludes the our just an overview on perturbation theory of eigenvalues of matrices. So thanks for your attention.
On behalf of IWM and UOH, I would like to sincerely thank all the participants for attending the mini course and making it a success. We are grateful to Professor Tanvi Jain for kindly accepting our invitation and delivering the lectures. We thank National Board of Higher Mathematics, NBHM, and Committee for Women in Mathematics for their continued generous support in funding the mini course. We would like to extend our heartfelt thanks to Professor Riddhi Shah, the chairperson of IWM, for her guidance and support. We would also like to express gratitude to Professor Ambar Habib for his constant support and suggestions. We thank Mr. Vinayak for his technical support, and we would like to thank University of Hyderabad for the support they provided. Thank you all again for your participation and support. We'll conclude this session.
I'll stop the recording now.
Yeah,
Yeah.
this YouTube also.
Yeah, I'll stop.